In October of 2025, NASA detected something that shocked the scientific community. Voyager 1, now 48 years old, sent back data revealing a discovery so extreme that it upended everything we thought we knew about the edge of our solar system. The spacecraft found a wall, not a physical wall, but a shell of superheated plasma reaching temperatures between 30,000 and 50,000 Kelvin. A blazing frontier where the sun's influence ends and interstellar space begins. Scientists called it a wall of fire, and Voyager 1 sailed right through it. But here is the truly astonishing part. Earlier this year, in May of 2025, NASA engineers did something that seemed impossible. They revived thrusters on Voyager 1 that had been dormant since 2004, 21 years of complete silence, 21 years of no activity, and yet, with a single command sent across 24 billion kilometers of empty space, the thrusters came back to life. The spacecraft that was supposed to die decades ago is still fighting, still sending data, still making discoveries that change how we understand the cosmos. And the story of how humanity sent two machines to the edge of everything and what those machines found out there begins not in the present, but in the past. It begins on a summer morning in 1977. On August 20th, 1977, two identical spacecraft sat on launch pads at Cape Canaveral. Their names were Voyager 1 and Voyager 2. They were about to be sent on a mission that would last far longer than anyone expected. A mission that would rewrite the textbooks on planetary science. A mission that would discover oceans beneath ice, active volcanoes on distant moons, magnetic fields that defied prediction, and ultimately reveal the nature of space itself at the very edge of human knowledge. But none of that was supposed to happen. The mission was designed to last just 5 years. That was the plan. 5 years to fly by Jupiter and Saturn. 5 years to gather data and come home. What changed everything was a cosmic accident of timing, a rare geometric arrangement of the outer planets. In the 1970s, astronomers had noticed something remarkable. Jupiter, Saturn, Uranus, and Neptune had aligned in a configuration that would not occur again for another 175 years. The next time this alignment would happen would be in the year 2152. By then, everyone alive today would be gone. This alignment was not just an interesting sight in the sky. It represented something far more profound. It represented a pathway through the solar system, a trajectory that a spacecraft could follow. Because of the precise positions of these planets, a spacecraft could use the gravity of Jupiter to accelerate toward Saturn, then use Saturn's gravity to fling itself toward Uranus, and then use Uranus to reach Neptune. It was a cosmic billiard shot, a grand tour of the outer solar system that would be virtually impossible to achieve at any other time in history. This gravity assist technique had been demonstrated before. NASA's Mariner 10 spacecraft had used it in 1973 and 1974 to visit Venus and Mercury. But the Voyager mission would be far more ambitious. A flight to Neptune without this gravity assist would take 30 years. Using gravity assists, the flight time could be reduced to just 12 years. NASA faced a critical decision. The mission was originally conceived to visit only Jupiter and Saturn, but the rare planetary alignment offered an opportunity that would not come again for centuries. NASA decided to build two spacecraft and attempt something audacious. They decided to explore 4 planets instead of 2. They decided to attempt to gather data that would take decades to fully understand. Voyager 2 was launched first, on August 20th, 1977. Voyager 1 followed 16 days later, on September 5th, 1977. Voyager 1 was launched on a faster, shorter trajectory than its twin. This meant that even though it launched second, it would arrive at Jupiter first and reach the outer planets faster. Both spacecraft were launched aboard Titangent Centaur expendable rockets. Each Voyager weighed 815 kilograms. Each one was roughly the size of a grand piano. Each one was built like a tank. They had to be. The journey ahead was not simply a matter of distance. It was a matter of survival in an environment that was fundamentally hostile to human machines. Think about your smartphone. The device you carry in your pocket has approximately 256 gigabytes of memory, 256 billion kilobytes. The entire computer brain of Voyager 1 had 65,000 bits of memory. Your smartphone is approximately 4 million times more powerful than the complete computational system of Voyager 1. And yet, with those 65,000 bits, engineers at the Jet Propulsion Laboratory had to program a spacecraft that could navigate autonomously across billions of kilometers. A spacecraft that could make scientific observations. A spacecraft that could make corrections to its course. A spacecraft that could repair itself when problems arose. All without the ability to communicate in real time. A signal from Earth takes more than 22 hours to reach Voyager 1. Another 22 hours for a response to come back. In almost 2 days of communication time, anything could go wrong. And in the depths of space, there was no way to fix it except by sending new commands from Earth. Commands that would take another 2 days to reach the spacecraft. The Voyager spacecraft were powered by plutonium, not solar panels, because the sun is too distant at the outer planets. Its light is just another star in the sky. The nuclear power source, called a radioisotope thermoelectric generator, converted the heat from radioactive plutonium decay into electricity. Each spacecraft carried about 10 kilograms of plutonium. This power source would keep the spacecraft alive for decades. The spacecraft carried scientific instruments, magnetometers to measure magnetic fields, spectrometers to analyze light, plasma wave detectors to measure charged particles, cosmic ray instruments, ultraviolet spectrometers, and cameras. Simple cameras. The cameras had no zoom, no digital enhancement, no way to store multiple images. They took pictures on film and then converted those images into data that could be transmitted across space at the speed of light. The story of Voyager is not a story about technology. It is a story about discovery, about what happens when you send machines into the unknown with only one objective: to find out what is there. In March of 1979, Voyager 1 reached Jupiter. What the spacecraft discovered there shattered assumptions that scientists had held for centuries. Jupiter is not simply a giant sphere of gas. It is a system. A complex, dynamic system filled with radiation and magnetic fields and storms that rage across the entire planet. The Great Red Spot had been observed from Earth for over 300 years. It is a storm, a hurricane so enormous that Earth could fit inside it 40 times over. But no one had ever seen it close up. No one had ever measured its winds. The Voyager 1 cameras captured the first detailed images of this storm. The first measurements showed wind speeds exceeding 400 meters per second, faster than any hurricane that had ever occurred on Earth. But the cameras also turned toward something far more significant: the moons of Jupiter. Scientists had known since the time of Galileo that Jupiter had moons, 4 large ones: Io, Europa, Ganymede, and Callisto. They were called the Galilean moons because Galileo discovered them in 1610 when he first pointed a telescope at Jupiter. but no one had ever studied them closely. No one knew what they were really like. Astronomers had looked at Jupiter from Earth for centuries. They had mapped its bands and zones. They had watched its storms. But the moons were just points of light, dots orbiting a giant planet. No one had any idea what they might be like up close. The first surprise came from Io. When the Voyager 1 instruments began measuring thermal radiation from Io, the data seemed wrong. The instruments appeared to be malfunctioning. Moons were not supposed to emit heat like that. They were supposed to be frozen, dead, covered in ancient impact craters that would remain unchanged for billions of years. But Io was different. Io was alive. A scientist at the Jet Propulsion Laboratory named Linda Morabito was analyzing navigation photographs when she noticed something unusual: an arc on the edge of Io, a small arc that appeared in multiple images. She checked the photographs again. The arc was real. It was not a star. It was not an instrument error. It was a plume, a volcanic plume erupting from the surface of a moon orbiting Jupiter. This was the first active volcano ever observed beyond Earth. The first direct evidence that geological activity was not unique to our planet. The implications were staggering. It meant that internal heat was being generated within this distant moon. It meant that moons could be geologically active. It meant that the solar system was far more dynamic and alive than anyone had imagined. Scientists discovered that Io had 9 active volcanoes, 9, and they were not small volcanoes. Plumes of sulfur dioxide were shooting 300 kilometers into the sky. Lakes of molten lava were visible on the surface. The discovery of volcanism on Io led to a scientific revolution in how researchers thought about planetary bodies. Before Voyager 1, scientists understood volcanoes as the result of planetary cooling and internal differentiation. A large body like Earth would have internal heat from radioactive decay. This heat would cause material to rise and fall within the planet's interior, creating convection. Eventually, some of this heat would be released through volcanoes. But this process was thought to be unique to large planets and moons. Small bodies, the thinking went, would cool quickly and become geologically dead. Io proved this theory was incomplete. Io is not a large moon. It is about the size of our moon. It is only about 3,600 kilometers in diameter, and yet it was the most volcanically active body in the entire solar system. More active than Earth. More active than any volcano on any world that humans had ever studied. The explanation came from studying Io's orbit. Io orbits very close to Jupiter. It experiences gravitational tidal forces from the giant planet. These tidal forces squeeze and stretch the moon as it orbits, generating internal heat through friction. This heat is so great that it keeps Io's interior molten. This is called tidal heating. And it completely changed how scientists thought about the interior of moons and small planets. The discovery of active volcanism on Io was only the first surprise at Jupiter. As Voyager 1 continued to study the Galilean moons, the cameras turned toward Europa. It was a world covered entirely in ice. Its surface was crisscrossed with cracks and darker lines. Scientists called these features linear formations that suggested something remarkable. The surface of Europa appeared to be young, not ancient, not geologically dead. The cracks indicated motion, movement, change. And if the crust was moving, if it was fractured and broken, it could only mean one thing. Beneath that icy crust, there was liquid water. Think about this discovery. Europa is only about 2,500 kilometers in diameter. Earth's moon is about 3,500 kilometers. Europa is actually smaller than our moon. And yet, scientists began to realize that Europa might contain more liquid water than all of Earth's oceans combined. 40 to 100 kilometers of ocean, all of it hidden beneath an ice shell, 15 to 25 kilometers thick, all of it in complete darkness, all of it in a world that orbits 490 million kilometers from the Sunday. The existence of liquid water on Europa raised a profound question. If there was liquid water, and if that water was warm enough, it might harbor life. This was not simply another discovery about a moon in the solar system. This was a fundamental shift in how scientists thought about the possibility of extraterrestrial life. It meant that life did not have to evolve on the surface of a world with sunlight. It could evolve in the deepest parts of an ocean, in places where heat from the interior of a world provided energy instead of sunlight, in places where simple chemistry could create complex molecules, in places where the conditions might be similar to the earliest oceans on ancient Earth. Europa transformed the question from where could life exist to where could life not exist. And it opened the door to a new field of research: astrobiology, the search for life beyond Earth. The other two Galilean moons revealed their own secrets. Ganymede, the largest moon in the entire solar system, showed evidence of a complex surface. Some regions were ancient and heavily cratered, showing that they had been unchanged for billions of years. Other regions showed younger, fractured terrain, suggesting more recent geological activity. Callisto showed an ancient, heavily cratered surface, suggesting it had been geologically quiet for most of its history. But perhaps the most important discovery at Jupiter was not about the moons themselves. It was about what the moons told us about the Jovian magnetosphere. The magnetosphere of Jupiter is enormous. It is the largest magnetic field in the entire solar system. Io, with its active volcanoes, was pumping material into this magnetosphere. Sulfur, oxygen, and sodium, apparently erupted by Io's volcanoes and sputtered off the surface by impact of high-energy particles, were detected at the outer edge of the magnetosphere. The discovery showed that activity on Io affected the entire Jovian system. Voyager 1 completed its Jupiter encounter in early April 1979, after taking almost 19,000 pictures and many other scientific measurements. Voyager 2 picked up where its sister spacecraft left off, arriving at Jupiter in late July 1979. Voyager 2's encounter continued into August. Together, the two spacecraft took more than 33,000 pictures of Jupiter and its 5 major satellites. But Jupiter was not the final destination. It was merely the first stop on a cosmic journey that would transform our understanding of the solar system. In November of 1980, Voyager 1 reached Saturn. Saturn is different from Jupiter. While Jupiter is brown and tan and orange with complex cloud formations, Saturn appears more serene. Its atmosphere has subdued contrasts and fewer color differences. But what Saturn lacked in visual drama, it made up for with mystery. The two Voyager-Saturn encounters occurred 9 months apart. Voyager 1 made its closest approach to Saturn on November 12, 1980. Voyager 2 arrived at Saturn in August 1981. Saturn's atmosphere is almost entirely hydrogen and helium. Voyager 1 found that about 7% of the volume of Saturn's upper atmosphere is helium, compared with 11% of Jupiter's atmosphere. Scientists had expected the internal helium abundance to be the same as Jupiter's and the Sun's. The lower abundance of helium in the upper atmosphere suggests that the heavier helium may be slowly sinking through Saturn's hydrogen. This might explain the excess heat that Saturn radiates over the energy it receives from the Sunday. Saturn radiates about twice as much energy as it receives from the Sunday. It is as if Saturn has an internal power source. And in some ways, it does. The internal heat is left over from Saturn's formation billions of years ago. One of Saturn's most remarkable features was its winds. The Voyagers measured winds near Saturn's equator at about 500 meters a second, that is 1,100 miles per hour. The wind blows mostly in an easterly direction. Strongest winds are found near the equator, and velocity falls off uniformly at higher latitudes. At latitudes greater than 35 degrees, winds alternate east and west as latitude increases. The dominance of eastward jet streams indicates that winds are not confined to the cloud layer. They must extend inward at least 2,000 kilometers, or about 1,200 miles, into Saturn's interior. Furthermore, measurements by Voyager 2 show a striking north-south symmetry that leads some scientists to suggest the winds may extend from north to south through the interior of the planet. Saturn's rings are perhaps its most spectacular feature. The rings are made of countless particles of ice and rock, ranging in size from dust grains to car-sized boulders. The Voyager spacecraft discovered that the rings have a complex structure. There are gaps in the rings. There are waves in the rings. There are features called shepherd moons, which are small moons whose gravity helps keep the ring particles contained. Voyager 1 spotted 3 previously unknown moons orbiting Saturn. These moons were named Atlas, Prometheus, and Pandora. The discovery of new moons in Saturn's ring system led to the discovery of many more moons in the decades to come. More than 80 moons orbit Saturn today. But perhaps the most significant discovery at Saturn was what Voyager 1 found on Titan. Titan is Saturn's largest moon. It is the second largest moon in the entire solar system. Before Voyager 1, Titan had been completely mysterious. Earth-based telescopes could not see through its thick, opaque atmosphere. But Voyager 1's instruments could peer through the haze. What they found changed our understanding of planetary bodies forever. Titan's atmosphere is thick. It is actually thicker than Earth's atmosphere in terms of surface pressure. It is made primarily of nitrogen, with traces of methane and other organic compounds. When Voyager 1's spectrometer analyzed the light coming from Titan, it detected complex organic molecules, hydrocarbons, molecules that are the building blocks of life on Earth. This discovery suggested that Titan might have liquid hydrocarbons on its surface, pools of methane or ethane, oceans of liquid compounds. The existence of these compounds on Titan, a world so cold that water would be frozen solid as rock, raised profound questions about the nature of chemistry and the conditions necessary for life. The observations of Titan led scientists to propose that Titan might be a frozen version of early Earth. Billions of years ago, Earth's atmosphere was very different from today. It was filled with methane and other organic compounds. Lightning and ultraviolet radiation from the sun would cause these compounds to react and form more complex molecules. These complex molecules might have been the precursors to life. Titan, frozen in time at a temperature of -179 degrees Celsius, might give us a window into Earth's past. It might show us what the early Earth looked like before life emerged. And it might show us how the chemistry necessary for life can arise in diverse environments. After Saturn, Voyager 1 was aimed toward interstellar space. Its trajectory, designed to send the spacecraft closely past Titan and behind Saturn's rings, bent the spacecraft's path inexorably northward out of the ecliptic plane, the plane in which most of the planets orbit the Sunday. This meant that Voyager 1 would not visit Uranus or Neptune. Its mission was complete. But Voyager 2 continued. Voyager 2 had been aimed at a point that would automatically send the spacecraft in the direction of Uranus. NASA provided additional funding to continue operating both spacecraft and authorized JPL to conduct a Uranus flyby. This extension of the mission was revolutionary. It meant that Voyager 2 would become the only spacecraft in human history to visit all 4 gas giants. Voyager 2 encountered Uranus on January 24, 1986. At its closest approach, the spacecraft came within 81,500 kilometers of Uranus's cloud tops, 50,600 miles. Before Voyager 2, Uranus was almost completely unknown. Earth-based telescopes could barely resolve the planet as anything more than a tiny blue disk. Astronomers knew that Uranus had moons. They knew it had a magnetic field, but beyond that, it was a mystery. What Voyager 2 found shocked the scientific community. Uranus is tilted. Its axis of rotation is tilted at an angle of about 98 degrees. This means that Uranus essentially rolls around the Sun like a ball. One pole points directly at the Sun for part of Uranus's year, and then 42 years later, the other pole points at the Sunday. No other planet in the solar system has such an extreme tilt. The origin of this tilt is unknown. Some scientists suggest that Uranus was struck by a massive impact billions of years ago, an impact that knocked the planet over. Others suggest that Uranus formed in a different orientation, and its tilt is a remnant of the early solar system's chaotic past. Whatever the cause, the result is unique. Because of this extreme tilt, Uranus's magnetic field is also unusual. The magnetic field is tilted at an angle of 59 degrees relative to Uranus's axis of rotation. On Earth, the magnetic field is aligned roughly with the axis of rotation. The north magnetic pole is near the North Pole, and the south magnetic pole is near the South Pole. But on Uranus, the magnetic poles are offset. This creates a magnetosphere that is highly distorted and dynamic. Voyager 2 also discovered that Uranus is far colder than expected. The temperature at the equatorial region, which receives less sunlight over a Uranian year, is nevertheless about the same as that at the poles. This is mysterious. The equator should be warmer. The poles should be colder. But on Uranus, temperatures are uniform. This suggests that there is complex circulation in Uranus's upper atmosphere, transporting heat around the planet. Voyager 2's images of the 5 largest moons around Uranus revealed complex surfaces. The cameras detected 11 previously unseen moons. Miranda, one of Uranus's moons, showed an extraordinarily complex surface. It appears to be made up of sections of different densities and compositions, as if Miranda had been torn apart by some massive impact and then reassembled by gravity in a chaotic jumble. The discovery of Miranda's strange surface suggested that moons could experience catastrophic collisions and survive. It suggested that the history of the solar system was more violent and chaotic than previously imagined. Several instruments studied Uranus's ring system, uncovering the fine detail of the previously known rings and 2 newly detected rings. The rings are much darker than Saturn's rings. They are more like dark ribbons than bright circles. Voyager data showed that the planet's rate of rotation is 17 hours, 14 minutes. This is remarkably fast for a gas giant. It means that Uranus is spinning rapidly, completing one rotation in less than 18 hours. After Uranus, Voyager 2 continued toward Neptune. The journey from Uranus to Neptune took 2 years. During this time, the spacecraft drifted through the outer solar system, instruments still active, still searching for data, still transmitting information back to Earth. In the summer of 1989, NASA's Voyager 2 became the first spacecraft to observe the planet Neptune. It was the final planetary target. The spacecraft was traveling at 19 kilometers a second, about 42,000 miles per hour, when it approached Neptune. It had taken 12 years of travel since leaving Earth in 1977, 12 years to reach a world that is 30 times farther from the Sun than Earth is. Voyager 2 passed about 4,900 kilometers, or 3,000 miles, above Neptune's North Pole. 5 hours later, Voyager 2 passed about 40,000 kilometers, or 25,000 miles, from Neptune's largest moon, Triton. Triton was the last solid body that Voyager 2 would have an opportunity to study. After Neptune, there were no more planets. There were no more moons. Just empty space. Endless empty space stretching all the way to the next star. Neptune is different from the other gas giants. Jupiter and Saturn are composed primarily of hydrogen and helium. But Neptune, along with Uranus, contains substantial amounts of water, methane, and ammonia ices. Neptune is cold. Its temperature at the cloud tops is about minus 214 degrees Celsius. But beneath the clouds, the pressure and temperature increase. Scientists believe that deeper in Neptune's interior, there may be a solid core of rock and ice. Neptune has the fastest winds of any planet in the solar system. Voyager 2 measured winds at the planet's equator reaching speeds of about 800 meters per second. That is more than 2,400 kilometers per hour. That is faster than the speed of sound on Earth. These winds blow primarily in an easterly direction, in the same direction that Neptune rotates. This is unusual. On Jupiter and Saturn, the fastest winds blow in both directions. But on Neptune, the winds are dominated by eastward flow. One of Neptune's most remarkable features is the Great Dark Spot. It is a storm system about the size of Earth. It is similar to the Great Red Spot on Jupiter, but it is temporary. When the Hubble Space Telescope observed Neptune years later, the Great Dark Spot had disappeared. Neptune has 13 known moons, but before Voyager 2, only 2 were known. Voyager 2 discovered 6 new moons orbiting Neptune. Among these moons, one stood out: Triton. Triton is Neptune's largest moon. It is about 2,700 kilometers in diameter, roughly the size of Earth's moon. Before Voyager 2, Triton was a complete mystery. Astronomers knew it existed, but they knew almost nothing about it. What Voyager 2 found at Triton was extraordinary. Triton is geologically active. At least, that was what the data suggested. The spacecraft detected what appeared to be cryovolcanoes. Volcanoes erupting not molten rock, but frozen nitrogen and methane. These eruptions shot plumes of nitrogen frost hundreds of kilometers into Triton's thin atmosphere. The nitrogen frost would then fall back onto the surface, accumulating in polar regions. Triton's surface showed complex geology. There were regions of old, cratered terrain and regions of younger features. There were ridges and valleys and strange formations that suggested tectonic activity. But perhaps the most surprising aspect of Triton was its orbit. Triton orbits Neptune in a direction opposite to Neptune's rotation. This is called retrograde orbit. This suggests that Triton was not formed around Neptune. It was captured. It was a world that formed elsewhere in the solar system and was captured by Neptune's gravity billions of years ago. When Voyager 2 flew past Triton, the spacecraft measured the moon's surface temperature using its infrared radiometer. The measurement showed temperatures around minus 235 degrees Celsius, colder than most places in the solar system. Yet, despite this extreme cold, Triton was geologically active. The discovery of geysers on Triton was unexpected. Geysers are fountains of material erupting from beneath the surface. On Earth, geysers erupt hot water and steam. But on Triton, geysers erupt nitrogen. The energy to power these geysers comes from the interior heat of the moon, combined with the heat from the distant sun and from tidal interactions with Neptune. It was yet another reminder that the solar system was far more active and dynamic than scientists had previously believed. After Voyager 2's Neptune encounter, both Voyager spacecraft were headed toward interstellar space. Voyager 1 launched on a faster trajectory and accelerated by Titan's gravity as it passed by Saturn. was moving at a rate of about 520 million kilometers per year. It was rising above the ecliptic plane at an angle of about 35 degrees. Voyager 2 was moving at a rate of about 470 million kilometers per year, diving below the ecliptic plane at an angle of about 48 degrees. Both spacecraft continued to study ultraviolet sources among the stars. Their fields and particles instruments continued to explore the boundary between the Sun's influence and interstellar space. Astronomers and engineers had to make difficult decisions about which instruments to keep active to extend the missions further. Power was limited. The radioisotope thermoelectric generators were slowly losing efficiency as their plutonium fuel decayed. So critical systems had to be shut down. Cameras were turned off. Infrared sensors were powered down. But the magnetometers kept running. The plasma wave detectors kept operating. The cosmic ray instruments continued their search for the boundary. In August of 2012, Voyager 1 crossed the heliopause. This is the boundary where the Sun's magnetic field ends and the interstellar magnetic field begins. Voyager 1 had entered interstellar space. The moment was marked by a sudden dramatic change in the data. The plasma wave instrument, which had been detecting charged particles from the Sun, suddenly detected a new population of particles. These were not particles from the Sunday, they were particles from interstellar space. They were particles that had come from other stars. They were cosmic rays from distant supernovae. They were remnants of the universe before our Sun was born. 6 years later, on November 5, 2018, Voyager 2 crossed the same boundary. It too entered interstellar space. The two Voyagers were now traveling through the local interstellar medium, the space between stars. The local interstellar medium is not empty. It contains gas, mostly hydrogen. It contains dust particles. It contains a magnetic field. And it contains cosmic rays. The cosmic rays are high-energy particles that travel through space at nearly the speed of light. They come from supernovae. They come from the cores of distant galaxies. They come from the violent events in the universe. As Voyager 1 and Voyager 2 traveled through this medium, they were making measurements that no human instrument had ever made before. They were measuring the density of the interstellar gas. They were measuring the strength of the interstellar magnetic field. They were measuring the flux of cosmic rays. They were measuring phenomena that scientists had previously only been able to study indirectly from Earth. One of the most intriguing discoveries was the detection of plasma waves. These are waves in the plasma, the ionized gas that fills the space between stars. Voyager 1 detected a mysterious hum, a low-frequency sound, frequencies around 3 kilohertz. The origin of this hum is still not fully understood. Some scientists believe it is related to the turbulence in the interstellar medium. Others believe it might be generated by magnetic field interactions. Whatever its origin, it is one of the great mysteries still waiting to be solved. As the Voyagers traveled further into interstellar space, they began to discover something unexpected. The density of the interstellar medium was increasing. In October of 2020, astronomers reported a significant, unexpected increase in density in the space beyond the solar system, as detected by the Voyager space probes. The increase in density suggests a large-scale feature of the very local interstellar medium, a wall, a region of higher density that extends across many light-years of space. One theory is that this wall is the edge of the local bubble. The local bubble is a region of space about 1,000 light-years across. It is a region of relatively low density. Inside the local bubble, the density of gas is much lower than in the surrounding interstellar medium. Scientists believe the local bubble was created by a supernova explosion billions of years ago. The explosion sent a shock wave through the interstellar medium, clearing a cavity creating a bubble of lower density space. Our solar system, it appears, is located inside this bubble, and the Voyagers are now detecting the walls of the bubble, the sharp boundary where the low-density bubble meets the higher-density space beyond. In the fall of 2022, Voyager 1 encountered a serious problem. The spacecraft's attitude articulation and control system began transmitting data that didn't match the state of the probe. The telemetry data was corrupted. The spacecraft was sending back information that made no sense. The spacecraft appeared to be malfunctioning, yet all the other instruments reported that everything was operating normally. For months, engineers and scientists at the Jet Propulsion Laboratory worked to solve the mystery. They analyzed data. They ran simulations. They tested hypotheses. It took them more than 9 months to figure out what had gone wrong. The problem, they eventually determined, was in one of the spacecraft's 3 onboard computers. One of the memory modules had been corrupted. A single bit had been flipped. 1 0 had become a 1, or 1 1 had become a 0. In a memory system of 65,000 bits, a single corrupted bit might seem like nothing. But it had enough consequence to corrupt the entire data stream coming from that computer. Finding the problem was one thing. Fixing it was another. The spacecraft was billions of kilometers away. Engineers could not simply open it up and repair it. They had to send commands across space. Commands that would take more than 22 hours to reach the probe, and then another 22 hours to hear the response. More than 2 days for a question and answer. But the engineers at JPL were skilled and patient. They worked through the problem methodically. They identified the corrupted memory location. They worked with Voyager 1 to isolate the problem and find a workaround. By June of 2024, they had successfully restored the spacecraft to full operation. Voyager 1 was sending good data again. This crisis, this near-death experience of a spacecraft that was 46 years old, demonstrated the ingenuity and dedication of human engineers. It showed that even at the edge of the solar system, even at distances where communication takes nearly a day, humans could reach out and keep their instruments alive. Then, in May of 2025, came the extraordinary news. NASA engineers had revived Voyager 1's backup thrusters. The spacecraft's main thrusters had stopped firing decades earlier, in the year 2004. Now, after 21 years of dormancy, they fired again. The spacecraft was using these backup thrusters to make slight adjustments to its orientation to help the spacecraft point its antenna back toward Earth. This would allow Voyager 1 to continue transmitting data for several more years. And just weeks after that thruster revival, Voyager 1 detected the temperature wall, the superheated plasma at the edge of the solar system. The heat reaching temperatures between 30,000 and 50,000 Kelvin, a blazing frontier that marks the boundary between the sun's realm and the universe beyond. The Voyagers have now been transmitting data for nearly 50 years. They have explored 4 planets and 48 moons. They have discovered active volcanoes beyond Earth. They have found evidence of hidden oceans. They have revealed the complexity and diversity of planetary magnetic fields. They have detected the hum of the interstellar medium. They have found the boundary of a vast bubble of gas that contains our solar system. And they continue to send data back to Earth, even now, at the age of 48 and 47. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of Gliese 445, a star that is approaching our solar system. In about 40,000 years, Voyager 2 will pass within 1.7 light-years of Ross 248, another nearby star. And in 296,000 years, Voyager 2 will pass within 4.6 light-years of Sirius, which is the brightest star in the night sky. The spacecraft are not expected to collide with a star for 1 sextillion years, 1 followed by 21 zeros. These two machines, built by human hands in the 1970s with computers less powerful than a pocket calculator, have become humanity's ambassadors to the stars. They carry with them the golden record, a golden phonograph record containing sounds and images from Earth, music from cultures around the world, greetings in 55 languages, the images and sounds of Earth, a message from humanity to any civilization that might find them. On the golden record is a message from Carl Sagan, a scientist who dedicated his life to the search for extraterrestrial life. He said, "This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours." The Voyagers are still attempting to survive, still sending data, still teaching us about the universe, and their journey is far from over. In the 25th century, in the 30th century, and for millennia to come, the Voyagers will continue their voyage through the stars, carrying humanity's message to worlds yet unknown. The discoveries made by Voyager 1 and Voyager 2 did not simply expand our knowledge of the solar system. They fundamentally changed how scientists think about planets, moons, and the conditions necessary for life. Let me walk you through the most important discoveries and explain why they matter. The first major discovery was the nature of volcanism and tidal heating. Before Voyager 1, scientists believed that only large bodies could sustain geological activity. The reasoning was straightforward. Small bodies cool quickly. Without internal heat, there is no geological activity. The Moon, which is about a quarter the size of Earth, showed virtually no geological activity. It was covered in ancient impact craters that had remained unchanged for billions of years. Mars, which is half the size of Earth, showed some evidence of past volcanism, but appeared geologically dead in the present. Scientists extrapolated from these observations and concluded that small moons orbiting distant planets would be geologically dead. They would be icy, frozen, and unchanging. Then, Voyager 1 found Io. Io is about the size of our moon. By conventional thinking, it should have been geologically dead, but it was not. 9 active volcanoes were erupting on its surface. Plumes of sulfur dioxide were shooting 300 kilometers into the sky. Lakes of molten lava were visible. The heat being generated on Io was extraordinary. Scientists estimated that the heat flux from Io's volcanoes exceeded that from all of Earth's volcanoes combined. This changed everything. The explanation came from studying Io's orbit and its interaction with Jupiter. Io orbits very close to Jupiter, about 420,000 kilometers away. Jupiter is an enormous planet, with a mass more than 300 times that of Earth. The gravitational pull from Jupiter on Io is enormous. And because Io orbits along with other large moons of Jupiter, the combined gravitational effects of these moons create tidal forces within Io. Tidal forces are not new. Earth's moon creates tidal forces on Earth. These forces cause the oceans to rise and fall, creating tides. But the tidal forces on Io from Jupiter are far more extreme. As Io orbits Jupiter, it is constantly squeezed and stretched by gravitational forces. This squeezing and stretching causes friction within Io's interior. Friction generates heat. This heat is so great that it keeps Io's interior molten, feeding volcanoes at the surface. The discovery of tidal heating on Io led to a revolution in planetary science. It showed that geological activity was not limited to large bodies. It showed that the orbital dynamics of moons could generate enough heat to sustain volcanism and, most importantly, It showed that scientists' understanding of where life might exist was incomplete. If a small moon orbiting a giant planet could be geologically active, it meant that other small moons could be too. It meant that the solar system was far more alive and dynamic than anyone had previously imagined. It meant that the inventory of places where life might exist had to be expanded. The second major discovery was the evidence for a subsurface ocean on Europa. Europa's surface is covered with ice. It appears smooth from a distance, but up close, it shows intricate detail. There are cracks, there are ridges, there are features that suggest movement and change. The surface appears young, not geologically dead. The cracks suggest that Europa's ice crust is dynamic. It is moving, stretching, fracturing. For this to happen, the ice must be floating on something. It must be floating on liquid water. Scientists estimate that beneath Europa's ice crust, which is about 15 to 25 kilometers thick, there is an ocean of liquid water about 40 to 100 kilometers deep. This ocean would contain more water than all of Earth's oceans combined. The existence of this ocean raised a profound question. If there is liquid water, and if that water is warm enough, could there be life? On Earth, we know that life requires liquid water. We also know that life requires chemical energy. On Earth, chemical energy comes from the sunday. Photosynthetic organisms use sunlight to create organic molecules. These molecules are then consumed by other organisms, releasing energy. This energy drives the entire web of life on Earth. But Europa's ocean is not illuminated by the sunday. It is hidden beneath an ice crust. No sunlight penetrates to the ocean below, so photosynthesis is impossible. But there could be another source of energy. The gravitational interactions between Europa and Jupiter could cause tidal heating, similar to what happens on Io. This internal heat could warm Europa's ocean, and in Earth's oceans, there are organisms that do not depend on sunlight. They depend on chemical energy. In the deepest parts of Earth's oceans, at hydrothermal vents, where hot water erupts from the Earth's crust, there are ecosystems that do not depend on photosynthesis. They depend on chemosynthesis. Bacteria break down chemical compounds like hydrogen sulfide and use the energy released to create organic molecules. These molecules feed a diverse ecosystem of organisms adapted to extreme conditions. Europa could have similar ecosystems. Hidden beneath the ice, in a dark ocean warmed by internal heat, chemical energy could support life. This possibility transformed the search for life beyond Earth. It meant that life did not have to exist on the surface of a planet with sunlight. It could exist in the depths of an ocean, on a frozen moon. The discovery of Europa's ocean opened new research directions. Scientists began to ask what conditions would be necessary for life to emerge and thrive on Europa. They began to plan future missions to explore Europa's surface and, eventually, to drill through the ice and sample the ocean below. In 2024, NASA selected the Europa Clipper mission, which will orbit Jupiter and make multiple close flybys of Europa, searching for signs of habitability and potential life. The third major discovery was the complex atmospheric chemistry of Titan. Titan is Saturn's largest moon. It is the second largest moon in the entire solar system. Before Voyager 1, Titan had been completely mysterious. The spacecraft spectrometer analyzed the light coming from Titan and detected complex organic molecules, hydrocarbons, molecules containing carbon and hydrogen. These are the same types of molecules that form the basis of life on Earth. The implications of this discovery were profound. Hydrocarbons are produced on Earth by living organisms and by the decomposition of dead organic matter. But on Titan, with its extreme cold and the absence of life, hydrocarbons were being produced by chemical reactions in the atmosphere. Ultraviolet light from the sun was causing methane molecules to react, creating more complex organic molecules. These molecules were then falling down to the surface, accumulating in layers. Scientists realized that Titan might be a frozen version of ancient Earth. Billions of years ago, Earth's atmosphere was very different from today. It was filled with methane and other organic compounds. Lightning and ultraviolet radiation would cause these compounds to react and form more complex molecules. These complex molecules might have been the precursors to life. Titan, frozen in time at a temperature of -179 degrees Celsius, might give us a window into Earth's past. It might show us how chemistry in a prebiotic atmosphere could produce the building blocks of life. Voyager 1 detected atmospheric constituents of Titan that included carbon monoxide, hydrogen cyanide, and methane. Later missions, particularly the Cassini-Huygens mission that arrived at Saturn in 2004, would discover that Titan's atmospheric chemistry was even more complex than Voyager 1 had suggested. Titan has liquid methane and ethane on its surface, forming seas and lakes, particularly in the polar regions. Beneath the surface, there is an ocean of liquid water. Titan presents a unique combination of conditions: complex organic chemistry in the atmosphere, liquid methane on the surface, a water ocean beneath the surface. This combination might provide the chemical environment necessary for life to emerge and evolve. While life on Earth is based on liquid water and carbon chemistry, life on Titan might be based on liquid methane and a completely different chemistry. This possibility expands the universe of potential habitats for life. The fourth major discovery was the unusual magnetic field of Uranus. When Voyager 2 approached Uranus in 1986, scientists expected to find a planet with a magnetic field similar to Jupiter and Saturn. They expected the magnetic field to be roughly aligned with the planet's axis of rotation. But Uranus surprised them. Uranus's magnetic field is tilted at an angle of 59 degrees relative to the planet's axis of rotation. This is an enormous tilt. On Earth, the magnetic field is nearly aligned with the axis of rotation. The north magnetic pole is near the north geographic pole. The south magnetic pole is near the south geographic pole. But on Uranus, the magnetic poles are almost perpendicular to the geographic poles. Furthermore, the center of the magnetic field is offset from the center of the planet. The magnetic dipole is not centered at Uranus's core. This creates an asymmetrical magnetosphere. Later analysis of the Voyager 2 data revealed that the magnetosphere of Uranus was heavily compressed on the side facing the Sun. This compression was caused by the solar wind, the stream of charged particles flowing out from the Sun. When Voyager 2 passed through this compressed magnetosphere, it detected high concentrations of energetic particles. These particles were more energetic than expected. Scientists had difficulty explaining their observations with conventional models of how magnetic fields trap and accelerate particles. New analysis of the Voyager data, conducted decades later in 2025, revealed that the unusual observations made by Voyager 2 were due to a cosmic coincidence. In the days just before Voyager 2's arrival, Uranus had been struck by an unusual type of space weather event. This event had temporarily squashed Uranus's magnetosphere, compressing it far more than normal. Voyager 2 had arrived during this rare event. If the spacecraft had arrived just a few days earlier or later, it would have observed a completely different magnetosphere. This realization was important because it showed how rare events can influence our observations. It also highlighted how our understanding of planets could be biased by the specific conditions that existed at the moment of observation. Uranus's magnetosphere is not always as compressed as Voyager 2 observed. The planet has a complex, dynamic magnetosphere that varies with solar activity. The fifth major discovery was the enormous winds on Neptune. When Voyager 2 approached Neptune in 1989, Scientists were surprised by the observations of wind speeds. Neptune orbits far from the Sunday. It receives very little solar energy. The Sun, as seen from Neptune, is just a bright star in the sky. It provides only 1/600th of the energy that reaches Earth. Neptune should be a calm, quiet place. But Neptune's winds are among the fastest in the solar system. Wind speeds reach 800 meters per second, more than 1,700 miles per hour. These winds blow faster than the speed of sound in Earth's atmosphere. They blow faster than any wind that could be generated by solar heating at such a distance from the Sunday. This discovery raised a fundamental question. Where is the energy coming from that powers these winds? Scientists realized that Neptune must have an internal source of energy. Like Saturn, Neptune radiates more energy than it receives from the Sunday. This internal energy comes from the planet's formation billions of years ago. Heat left over from accretion, gravitational compression, radioactive decay. Whatever the source, this internal heat must be generating the powerful winds on Neptune. The discovery of Neptune's winds showed that planetary atmospheres are not simple systems where wind speed is directly related to solar heating. It showed that planets could have complex internal structures that drive atmospheric circulation. It showed that there were still mysteries in our understanding of gas giants. The sixth major discovery was the nature of the heliopause and the boundary of the solar system. For decades, astronomers had debated where the solar system ended. The Sun's gravity extends far into space. Its magnetic field extends even farther. But there must be a boundary where the Sun's influence ends and the interstellar medium begins. This boundary is called the heliopause. As Voyager 1 and Voyager 2 traveled outward, they were searching for this boundary. Scientists knew it was out there somewhere, but they didn't know where. Some thought it might be just beyond Pluto. Others thought it might be much farther out. The estimates varied widely. When Voyager 1 detected a sudden change in the plasma in August of 2012, scientists realized that the spacecraft had crossed the heliopause. The plasma density increased by a factor of 40. Suddenly, the spacecraft was detecting particles from interstellar space instead of solar wind particles. The crossing of the heliopause was marked by precise measurements. The plasma wave instrument on Voyager 1 began detecting locally generated electron plasma oscillations at a frequency of about 2.6 kilohertz. This frequency corresponds to an electron density of about 0.08 particles per cubic centimeter. This is very close to the expected density of the interstellar medium. Other instruments confirmed the crossing. The cosmic ray detector began detecting fewer high-energy particles because the solar wind no longer blocked cosmic rays from reaching the spacecraft. The magnetic field measurements changed. The direction of the magnetic field shifted. Scientists realized that the heliopause was located at a distance of about 120 astronomical units from the Sunday. 1 AU is the distance from Earth to the Sun, about 150 million kilometers. So the heliopause is about 18 billion kilometers from the Sunday. It took Voyager 1 35 years to reach this boundary. When Voyager 2 crossed the heliopause 6 years later, in November of 2018, it crossed at a similar distance, about 119 astronomical units from the Sunday. This suggested that the heliopause is roughly spherical, at least at these 2 points where the Voyagers crossed. The crossing of the heliopause was not a simple transition from one region to another. Instead, there is a transition region called the heliosheath. In this region, the solar wind is slowing down as it approaches the heliopause. There is turbulence. There is a magnetic field that is tangled and complex. Voyager 1 took several years to traverse the heliosheath. Voyager 2 took several years as well. The discovery of the heliopause and the structure of the heliosheath revealed something important about the solar system. The solar system is not simply the sun plus planets plus moons. It is a dynamic system with a defined boundary. The solar wind, a stream of charged particles flowing out from the sun, creates a bubble called the heliosphere. This bubble extends to the heliopause. Beyond the heliopause is the interstellar medium. The seventh major discovery was the nature of the local bubble. Once Voyager 1 crossed the heliopause and entered interstellar space, it began making measurements that no human spacecraft had ever made before. It was measuring the properties of the interstellar medium directly, rather than from a distance. The density of the interstellar medium was higher than the outer heliosphere, but it was still extraordinarily thin, about 0.1 particles per cubic centimeter. This is an extraordinarily good vacuum by Earth standards, but it is dense compared to the outer heliosphere. As the Voyagers traveled deeper into interstellar space, they began to detect a mysterious structure. The density was increasing. This seemed strange. Scientists would have expected the density to be relatively uniform across interstellar space. But the Voyagers were detecting regions of higher and lower density. The answer came from understanding the local bubble. The local bubble is a region of space about 1,000 light-years across. It is a region of relatively low-density gas. Astronomers believe the local bubble was created by a supernova explosion billions of years ago. The explosion sent a shock wave through the interstellar medium. The shock wave cleared a cavity, created a bubble of low-density space. Our solar system is located inside this bubble. The Voyagers are now approaching the boundary of the local bubble. The spacecraft are detecting increasing density as they approach the wall of the bubble. The wall is not sharp. It is a transition region. But the density increase is significant. Scientists have suggested that Voyager 1 has detected temperature increases that might be associated with shock waves or other dynamic phenomena at the boundary of the local bubble. These 7 discoveries represent some of the most important findings from the Voyager missions. They have transformed our understanding of planetary science, astrobiology, and the structure of the solar system and the local neighborhood of interstellar space. They have opened new research directions. They have inspired new missions. And they continue to teach us about the cosmos. In November of 2023, something unexpected happened. Voyager 1, the spacecraft that had been transmitting data from the edge of the solar system for 46 years, suddenly began sending back gibberish, meaningless data, ones and zeros that made no sense. The engineers at the Jet Propulsion Laboratory in Pasadena, California, stared at their screens in disbelief. A spacecraft that had been functioning for nearly half a century was now sending information that could not be interpreted. For 22 hours, the spacecraft continued to send garbled data. During those 22 hours, the engineers did not know if the problem was a temporary glitch or a permanent failure. They did not know if this was the beginning of the end for Voyager 1. The spacecraft was 24 billion kilometers away. The distance to send a command and receive a response was nearly 45 hours. Any repair would take months. But the engineers at JPL had solved problems like this before. They knew how to think, how to analyze data, how to work methodically through complex systems. So they began to search for the source of the problem. The first clue came from comparing the garbled data to data that had been sent before the problem began. The engineers looked for patterns. They looked for similarities. They looked for any indication of what had changed. The data format appeared to be wrong. The structure of the information seemed corrupted. But where? In what system? Voyager 1 has 3 computers. The Flight Data Subsystem, or FDS, is responsible for collecting data from all the scientific instruments and packaging it for transmission to Earth. The FDS takes information from the magnetometer, the plasma wave detector, the cosmic ray detector, and other instruments. It collects all this information and formats it into a data stream that can be transmitted back to Earth through the spacecraft's antenna. The engineers hypothesized that the problem was in the FDS. They sent commands to the spacecraft to restart this computer system. But the restart did not solve the problem. The data was still corrupted. Then, in March of 2024, the team sent a special command. They called it a poke. The poke was designed to read the memory of the FDS computer and transmit that memory back to Earth. The team wanted to see exactly what was stored in the computer's memory. They wanted to see if they could identify where the corruption was occurring. The response came back after 22.5 hours of travel time in each direction. 45 hours after sending the command, the engineers received the memory readout, and they could see it immediately. About 3% of the FDS memory was corrupted. 3%. In a system of 65,000 bits, about 2,000 bits were wrong. Ones had become zeros. Zeros had become ones. And these corrupted bits rendered the entire memory system unable to function correctly. The team determined that the corrupted code was located on a single chip. A single computer chip out of dozens of chips in the FDS had failed, and the failure of this one chip had corrupted the data from the entire spacecraft. But here is where the story becomes remarkable. The chip could not be repaired. It was billions of kilometers away, encased in a spacecraft traveling at 56,000 kilometers per hour through the vacuum of interstellar space. There was no way to physically fix it, so the engineers did something creative. They decided to relocate the code. The corrupted chip contained essential software that the FDS needed to function, but the code could be moved. It could be divided into sections. Those sections could be stored in different places in the FDS memory, different locations that were not corrupted, different chips that still worked. But moving the code was not simple. The code had to be broken into pieces. Each piece had to be modified to work in its new location. References to where the code was located had to be updated throughout the FDS software. Everything had to be coordinated. Everything had to work together. The team started with the code responsible for packaging the spacecraft's engineering data. They divided this code into sections. They placed each section in a new location in the FDS memory. They updated all the references. They sent the commands to the spacecraft, and they waited for the response. 45 hours later, the response came back. The modification had worked. For the first time in 5 months, the FDS was sending intelligible data about the health and status of the spacecraft. The engineers could see voltage readings, current readings, temperature readings, all the data that told them whether the spacecraft was healthy. Over the following weeks and months, the team repeated this process. They relocated the code responsible for sending science data. They repositioned code after code after code. Each modification took weeks to plan, days to execute, and 45 hours to verify. But slowly, systematically, Voyager 1 was brought back to life. By the summer of 2024, Voyager 1 was transmitting science data again. The crisis had passed. The spacecraft was alive. The communications were clear. The data was intelligible. Voyager 1, at the age of 46 years old, was still functioning, still exploring, still teaching us about the cosmos. But the engineers knew that the problems were not over. They were just beginning. In the years that followed, the team identified another problem. The spacecraft's main thrusters were showing signs of age. These are small thrusters, not the big main engine that propelled the spacecraft through the solar system decades earlier. These small thrusters are used to orient the spacecraft, to keep the antenna pointed at Earth, to maintain the spacecraft's attitude in space. The primary thrusters work by expelling a small amount of propellant to generate thrust. Over the decades, this propellant has been sitting in the thruster's tubes. It has been exposed to radiation. It has been subjected to extreme temperatures. And it has started to congeal, to thicken, to build up residue that could, in time, clog the thrusters completely. If the primary thrusters stopped working, there was a backup. A set of backup thrusters that had been installed on the spacecraft in 1977. They had never been used. They had been dormant for almost 50 years. So dormant, in fact, that engineers were not sure they would still work if they were called upon. The backup thrusters had last been used in 2004, 20 years earlier. For 20 years, they had been sitting, unused, in the harsh environment of interstellar space. No one knew if they would function. No one knew if the propellant in the backup thrusters was still usable. No one knew if anything on the backup thrusters still worked, but they had to try. In May of 2025, the team at JPL made the decision. They would attempt to revive the backup thrusters. If they succeeded, Voyager 1 would have a backup system that could keep the spacecraft pointed at Earth for years to come. If they failed, nothing would be lost. The spacecraft was already aging. It was already showing signs of stress. But it was worth the attempt. The team sent commands to the spacecraft. Commands that would fire the backup thrusters for the first time in 21 years. The commands traveled across 24 billion kilometers of empty space. They took 22.5 hours to arrive. The team waited. They did not know what would happen. They did not know if the thrusters would respond. They did not know if anything would happen at all. 45 hours later, the signal came back. The thrusters had fired. They had responded to the commands. They had worked. After 21 years of dormancy, after 50 years of exposure to the harsh environment of interstellar space, the backup thrusters on Voyager 1 had come back to life. The team celebrated. It was a remarkable achievement. It was another lease on life for Voyager 1. The spacecraft that was supposed to die decades ago had just been given additional years of operation. The spacecraft that launched in 1977 was still fighting, still transmitting, still exploring. But the triumph of the thruster revival was soon followed by another discovery. A discovery so extraordinary that it seemed almost impossible. In October of 2025, just weeks ago, Voyager 1 sent back data revealing something unprecedented. The spacecraft had detected a region of extremely high temperature, a shell of superheated plasma. Temperatures ranging from 30,000 to 50,000 Kelvin. For reference, the surface of the Sun is about 5,800 Kelvin. This plasma was 5 to 10 times hotter than the surface of the Sunday, but Voyager 1's original plasma detector had stopped working years earlier. So how could the spacecraft be detecting plasma? How could it be measuring temperature in a region where the instruments designed to measure these things no longer functioned? The answer came from using the spacecraft's remaining instruments creatively. Two instruments that were still operational were the cosmic ray detector and the magnetic field sensor. These instruments were not designed to measure plasma temperature directly, but they could detect the effects of plasma. When the cosmic ray detector measures fewer high-energy particles, it suggests that those particles are being blocked by plasma or magnetic fields. When the magnetic field sensor detects changes in the magnetic field direction and strength, it suggests that the probe is entering a region with different properties. The team at JPL combined data from these two instruments. They combined it with data from other sensors, and they constructed a picture of what was happening around Voyager 1. The picture showed a region of extreme conditions. A collision zone. The solar wind, a constant stream of charged particles flowing out from the sun, was colliding with the interstellar medium. The interstellar medium is the gas and dust that fills the space between stars. It has its own magnetic field, its own temperature, its own pressure. When the solar wind collides with the interstellar medium, the collision creates turbulence. The magnetic fields compress. The particles are accelerated. Their velocities increase dramatically. And when particles move at extremely high velocities, they transfer energy. This energy appears as temperature. The region that Voyager 1 had detected was this collision zone. This is not a solid wall. There is no barrier made of material. It is a region, perhaps only 1 astronomical unit thick, where the solar wind and the interstellar medium are meeting. It is a cosmic blast furnace. It is a thin shell where temperatures reach between 30,000 and 50,000 Kelvin. But here is the remarkable part. Despite these extreme temperatures, Voyager 1 was unharmed. The spacecraft's hull did not overheat. The spacecraft's systems did not malfunction. The reason is that although the temperature is extreme, the density of matter in this region is extraordinarily low. In the vacuum of space, density and temperature are different properties. You can have extremely high temperature with extremely low density. On Earth, if you put your hand in water at 100 degrees Celsius, you will be severely burned. But if you put your hand in steam at 100 degrees Celsius, you will experience much less damage because the density of the steam is much lower than the density of the water. Similarly, in this plasma shell at 30,000 to 50,000 Kelvin, the density is so low that the energy transfer to the spacecraft is minimal. The spacecraft passes through it unharmed. Voyager 2, following its own path through interstellar space, also detected this phenomenon. The same pattern appeared in Voyager 2's data, the same temperature signature, the same magnetic field alignment, the same cosmic ray signature. This confirmed that what the Voyagers were detecting was a real phenomenon. It was not an instrumental error. It was not a temporary anomaly. It was a fundamental feature of the boundary between the solar system and interstellar space. The discovery of this plasma shell was surprising for another reason. Scientists had predicted that the magnetic field outside the heliopause, outside the solar system's boundary, would be oriented differently from the magnetic field inside the heliosphere. They expected a sharp change in direction. But the data from both Voyagers showed something unexpected. The magnetic field outside the heliopause was nearly parallel to the magnetic field inside the heliosphere. The magnetic field had rotated, but not as much as expected. This discovery suggests that our understanding of magnetic fields in space is incomplete. It suggests that the interaction between the Sun's magnetic field and the interstellar magnetic field is more complex than previously thought. It suggests that there are physical processes occurring at the heliopause that we do not yet fully understand. The Voyager spacecraft, now at the age of 48 and 47 years old, continue to explore. They continue to make discoveries. They continue to teach us. They continue to surprise us. In the decades to come, both Voyagers will continue to transmit data. The plutonium in their power sources will continue to decay. The instruments will continue to fail, one by one. But the most robust instruments will keep operating. They will continue to measure the properties of interstellar space. They will continue to detect plasma waves. They will continue to measure cosmic rays. They will continue to measure the magnetic field. Scientists estimate that Voyager 1 will continue to send data until about 2030. In 5 years, the spacecraft will still be active. After that, as the power supply weakens, instrument after instrument will be turned off. Eventually, only the most essential systems will remain, and then, even those will fade away. The power will drop below the threshold necessary to run the remaining systems, and Voyager 1 will go silent. But even then, it will not be the end. Voyager 1 will continue to coast through interstellar space. It will continue to travel toward other stars. In 40,000 years, it will pass within 1.6 light-years of Gliese 445. In 296,000 years, it will pass within 4.6 light-years of Sirius. And if, in those distant times, if a civilization has arisen on one of the planets orbiting one of these stars, if they have developed the technology to detect and understand what is approaching, they will find the golden record. They will discover the sounds of Earth, the music of human culture, the greetings in 55 languages. They will hear Carl Sagan's message, a message from a small, distant world, a message that says, we were here, we cared, we wondered, we tried to reach out and connect with the universe. That is the legacy of Voyager 1 and Voyager 2. Not simply the scientific discoveries, not simply the data that transformed our understanding of planetary science and astrobiology, but a message, a statement about humanity, a statement that we are curious, we are ambitious, we are willing to send our machines into the unknown, and we are hopeful that somewhere, somehow, someone will listen. The story of Voyager does not end with the discoveries. It does not end with the scientific data or the crisis that nearly destroyed the mission. The true story of Voyager is about what it means, what it represents, and what it will do for billions of years to come. When Voyager 1 and Voyager 2 were launched in 1977, they were designed as explorers, machines sent to gather data about distant worlds. But they became something more. They became ambassadors, symbols of human ambition and human hope. And they carried with them a message to the stars. On each spacecraft is the golden record, a phonograph record made of gold, 11.5 inches in diameter. It contains 55 minutes of music, greetings in 55 languages, images of Earth, sounds of Earth, a message from humanity to any civilization that might, in the distant future, find the spacecraft. The golden record was the idea of Carl Sagan, the famous astronomer and science communicator. Sagan believed that if humanity was going to send machines into the cosmos, those machines should carry a message. Not a message from the government, not a message from any particular nation, but a message from humanity, from all of us, a representation of the diversity of human culture and human achievement. The record contains music from around the world: Bach, Beethoven, Mozart, jazz, raga from India, Aboriginal songs from Australia, a Peruvian panpipe, Mozart's Queen of the Night aria from the Magic Flute, Louis Armstrong singing "What a Wonderful World," and many others. The images show scenes of Earth, a sunrise over the ocean, children playing, farmers harvesting crops, a breastfeeding mother, a heart surgery, scientists working in laboratories, factories, crowds of people in public squares, dancers, musicians, the diversity of human experience. The greetings are in 55 languages: English, Spanish, French, German, Russian, Japanese, Chinese, Arabic, and many others. In each language, representatives of that language group recorded a greeting, a simple message saying, "Hello," saying, "We are here," saying, "We are reaching out." There is a greeting from the United Nations Secretary General at the time. There is a greeting from the President of the United States. But most importantly, there are greetings from ordinary people, from children, from people speaking in languages from every part of the world. It is a statement that humanity is diverse, that we speak many languages, that we value our differences. On the record is a message from Carl Sagan. He says, "This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours." Simple words, but profound. An expression of hope, an expression of the human desire to connect, to reach across the void of space and touch something beyond ourselves. The golden record may never be found. The chances of another civilization encountering Voyager in the vastness of space are extraordinarily small. But that does not diminish its importance. The record exists. It exists as a statement about who we are. It exists as a hope for the future. It exists as a message that will outlast Earth. It will outlast the Sunday. It will continue to exist for billions of years, carrying our message into the cosmos. The scientific legacy of the Voyager missions is equally profound. The discoveries made by these two spacecraft transformed our understanding of the solar system. They revolutionized planetary science. They opened new fields of research. They inspired the missions that followed. Before Voyager, Jupiter was known to have 4 large moons. After Voyager, scientists knew that those moons were worlds, individual worlds with complex geology. Europa had an ocean. Io had volcanoes. Ganymede and Callisto had their own unique characteristics. This knowledge inspired the Galileo mission, which arrived at Jupiter in 1995. Galileo spent 8 years studying Jupiter and its moons, building on the foundation laid by Voyager. The discovery of Titan's complex atmospheric chemistry inspired future missions. The Cassini-Huygens mission arrived at Saturn in 2004 and spent 13 years studying the planet and its moons. Cassini made detailed observations of Titan. It found that Titan had liquid methane lakes. It found that Titan's atmosphere was even more complex than Voyager had suggested. And it found evidence of cryovolcanoes on Enceladus, another of Saturn's moons. The discovery of Europa's subsurface ocean inspired a generation of scientists to think about ocean worlds. Europa became the symbol of the search for extraterrestrial life. It became the focus of intense research and planning. And now, in 2024, Europa Clipper has launched to study Europa in unprecedented detail. Europa Clipper will arrive at Jupiter in 2030 and will conduct 49 close flybys of Europa. It will measure the thickness of Europa's ice shell. It will study the composition of the ice and the materials that may be rising from the ocean below. It will search for signs of habitability. Europa Clipper carries its own message inspired by the golden record on Voyager. It carries a plaque with the names of 2.6 million people. It carries a poem written by U.S. Poet Laureate Ada Limon titled "In Praise of Mystery, a Poem for Europa." It carries the word water written in 103 languages, with sound waves representing the pronunciation of the word in each language. It carries the symbol for water in American Sign Language. It is a tribute to the Voyagers. It is a continuation of the Voyager legacy. The Voyagers also revolutionized how scientists think about comparing planets. The field of comparative planetology grew out of Voyager observations. Scientists realized that studying planets by comparing them to each other could reveal patterns, could reveal how planets form, could reveal how atmospheres evolve, could reveal the diversity of worlds that are possible. The Voyager observations showed that Earth is not unique. Geological activity is not unique to Earth. Magnetic fields exist on many planets, but with different configurations. Atmospheres exist on many worlds, but with different compositions. Clouds exist on many planets, but with different structures. By comparing Earth to Venus, Mars, Jupiter, Saturn, Uranus, and Neptune, scientists could better understand what made Earth special. Before the Voyagers, many of these planets were almost unknown. We had theories about them based on observations from Earth. But the theories were often wrong. Jupiter was not what we expected. Saturn's rings were more complex than we thought. Uranus had a tilted magnetic field. Neptune had extreme winds. The solar system was far more complex and diverse than anyone had imagined. This realization had profound implications for the search for extraterrestrial life. If the solar system was this diverse, with such a variety of conditions on different worlds, then perhaps extraterrestrial life could exist in forms we had not imagined. Perhaps life could exist in the darkness of a subsurface ocean. Perhaps life could exist in the extreme cold of a frozen moon. Perhaps life could exist in environments that would kill any Earth organism. The Voyagers also inspired a new way of thinking about the possibilities for human civilization. They showed that humanity could create machines that could survive in harsh environments for decades. Machines that could be repaired remotely from billions of kilometers away. Machines that could make discoveries that changed our understanding of reality. The Voyagers demonstrated human ingenuity, human persistence, human curiosity. They showed that we could dream big and achieve those dreams. They showed that we could send machines to explore the solar system and return knowledge that transformed our understanding of the universe. Now, in the 21st century, the Voyagers continue to inspire. They continue to function. They continue to transmit data. They continue to make discoveries. And they continue to remind us that we are capable of extraordinary achievements. In the future, as the Voyagers travel through interstellar space, they will continue to measure the properties of the local interstellar medium. They will continue to detect cosmic rays. They will continue to measure magnetic fields. They will continue to transmit data back to Earth as long as the power holds out. Scientists estimate that Voyager 1 will continue to send data until approximately 2030, about 5 years from now. After that, as the plutonium power source decays, instruments will be turned off one by one. The spacecraft will become progressively less capable. Eventually, it will go silent. The power will fall below the threshold necessary to operate the transmitter, and Voyager 1 will stop talking to Earth. But that will not be the end of Voyager 1. The spacecraft will continue to travel through the cosmos. It will continue to move through interstellar space at about 56,000 kilometers per hour. In 300 years, it will reach the Oort cloud, a vast shell of icy bodies surrounding the solar system. The Oort cloud is thought to be the source of long-period comets. It is a region that extends almost halfway to the nearest star. It will take Voyager 1 about 300 years to reach the inner edge of the Oort cloud, and it will take another 30,000 years to traverse the Oort cloud. 30,000 years. In that time, the spacecraft will be moving through a region filled with icy bodies and dust. The interactions with these materials could potentially damage the spacecraft. But given the vast distances in space, encounters with objects are extremely rare. Scientists estimate that Voyager 1 will likely pass through the Oort cloud, essentially unharmed. After leaving the Oort cloud, Voyager 1 will continue into true interstellar space. It will travel toward the star Gliese 445, which is currently about 18.5 light-years away. In approximately 40,000 years, Voyager 1 will pass within 1.6 light-years of this star. 1.6 light-years is about 15 trillion kilometers. But that is not the end of the journey. Voyager 1 will continue traveling for millions of years, hundreds of millions of years, billions of years. Eventually, billions of years in the future, the Voyagers may encounter other stars. They may travel far enough to escape the Milky Way galaxy. They may travel for trillions of years. And through all of this time, the golden record will survive. Scientists have studied the question of how long the golden record might survive in interstellar space. They have calculated that the exterior-facing side of the record might become indecipherable after about 5 billion years of exposure to interstellar matter. But the side of the record that faces the spacecraft, the side that is protected, is likely to survive much longer, perhaps until the Milky Way collides with the Andromeda galaxy approximately 5 billion years in the future. Even if the record eventually becomes unreadable, even if the information becomes corrupted by cosmic radiation and impacts with interstellar dust, the physical record will still exist. It will still be there. It will still be a testament to the civilization that created it. Still be a message from Earth. Still be a token of what humanity was. The Voyagers represent something fundamental about the human spirit. We are explorers. We are curious. We are willing to send our machines into the unknown to find out what is there. We are willing to take risks, to attempt things that have never been attempted before, to reach beyond our grasp in hopes of touching something greater than ourselves. The Voyager missions cost about $856 million. For that cost, we sent 2 spacecraft to explore 4 planets. We discovered oceans beneath the ice. We discovered volcanoes on distant moons. We revealed the boundaries of the solar system. We measured the properties of interstellar space. And we sent a message to any civilization that might find it. We were here. We cared. We wondered about the universe. And we reached out. That is the legacy of Voyager. Not just the discoveries, not just the data, but the message. The statement about humanity. The statement that we are capable of dreaming, of achieving, of reaching toward the stars and attempting to touch them. In the future, other spacecraft will follow. New missions will be sent to explore the solar system and beyond. Humans may eventually travel to Mars. They may establish settlements on the moon. They may send probes to distant exoplanets. They may eventually meet extraterrestrial life. But they will all be standing on the shoulders of those who came before. They will all be building on the foundation laid by Voyager. The Voyagers showed the way. They showed that it was possible. They showed that humanity could create machines capable of surviving the harsh environment of space for decades. They showed that we could make discoveries that transformed our understanding of reality. They showed that we could succeed. And they continue to send signals. 48 years after launch, Voyager 1 is still transmitting, still exploring, still teaching us, still reminding us of what humanity can achieve when we dream big and work to make those dreams a reality. The Voyagers are no longer the newest spacecraft. They are no longer cutting-edge technology. By modern standards, they are ancient. But they endure, they survive, they continue. And in that continuation, in that persistence, they inspire us. They show us that the pursuit of knowledge is worth it, that exploration is worth it, that reaching toward the stars is worth it. Voyager 1 and Voyager 2 are now more than 50 years old. They are slowing down. Their power is fading. Their instruments are wearing out, but they are still alive, still fighting, still exploring. And when they finally go silent, when the last of the plutonium power source has been consumed, when the last transmission has been sent, they will still be traveling. They will still be carrying their message. They will still be Earth's ambassadors to the cosmos. That is the future of Voyager. Not a future that ends, but a future that continues. a future that extends for billions of years, a future that will take these machines to places we have never been, a future that will carry humanity's message to worlds we may never visit, a future that is, quite literally, infinite. The story of Voyager is not ending. It is continuing.